Hi, everybody. This is our last lecture of the week. It took me longer to make. I'm not done even making it now. I think it'll take longer for you to watch. There will only be two questions, one math problem, one summary kind of paragraph. So that's good for you, but it probably will take 45 minutes to watch. We'll see how it goes. Topic is simultaneity, meaning that if you have two events and they happen at the same time, we would consider them simultaneous. In the theory of relativity, we now understand that just because two things happen at the same time in one reference frame does not mean that they're simultaneous in all reference frames. In fact, there's a large class of categories, a class of events, for which if they are happening at the same time in one reference frame, they cannot be simultaneous in other reference frames. So that's what we're going to talk about. It's strange. First, what is time dilation? That concept is if, in order for the theory of relativity to work, what we've had to do is trade some things. In order for the theory of relativity to be real, and by the way, we think it is one of the most tested, the most highly challenged and analyzed branches of physics in history, and it holds up. We believe it really is a better understanding of our world. So given the theory of relativity, we have to let go of some things we assumed were right, and we find that actually are only telling us part of the picture. Some of the things that we thought were absolute and could never change, in fact, do, and they include time. Time isn't consistent. It doesn't advance at the same rate in all situations, and space itself is. We're going to start today talking about length contraction and how space is different in different situations. Okay, so time dilation is talking about that contraction, expansion of time depending on one's motion. And we were introduced to it by bringing up the twin paradox. We're going to finish talking about that today. Here's the twin paradox. Well, no. Here's the example we used to talk about time dilation, the fact that time can expand and contract depending on your motion. We have two situations. One reference frame is the observer on Earth looking up at a rocket ship that whizzes past. Both the observer and the rocket ship have with them in their reference frames a special clock. It's a light clock, and it's sort of like pendulum going back and forth, except for it's a light beam which is emitted out of the bottom, reflected off the top, bounces back to the bottom, and just keeps going ding, 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 bouncing back and forth at exactly the speed of light, which, because the law of physics tell us, it cannot change. That is absolute. The rate, the speed of light, is measured the same by all observers and all reference frames. So they would all agree, like, oh yeah, that's identical. That doesn't change. So person on Earth has a little light clock. Rocket whizzing past has one, but the rocket is moving. So now there's two motions, one up and down in the clock, and then there's the motion of the rocket ship. So the observer on Earth sees the light beam leave the bottom of the clock, bounce off the top, hit the bottom again. Because of the combined motion, now the rocket's in a different place. That light beam must have had to go at some sort of diagonal, some sort of hypotenuse of a triangle, and so it covered a greater distance. This would be shorter, but this is longer, and yet it does so at the same rate. So they're still in sync. The two clocks are still doing this, although one of them is actually in motion. That light beam travels a greater distance. They're still in sync, and yet that light beam is traveling exactly the same rate. The speed is the same. It arrives at the finish line at the exact same time, and yet it went farther. How is it possible to go the same speed and a farther distance and stay in sync? It isn't if you use traditional thinking. It is now that we understand that one of the things that can change is time itself. So the rocket ship is experiencing this motion at some fraction of the speed of light, and time in that reference frame is slower. It gets so complicated soon. Get ready. Okay, so we talked about that. That was the introduction to time dilation. Now, I want to remind you, our definition of the law of relativity is that all the laws of physics are the same everywhere. Specifically, the laws of physics, including the speed of light, are the same in all reference frames in continuous motion. Okay. Now, this is really important, and it's hard. I'm going to try and remind you and myself that when speaking about relativity, you can't say, okay, but one situation is real, and then this is kind of weird situation traveling at 90% the speed of light. They're both real situations, and their realities are both valid. So you can't say, well, cool, about time dilation, observer on Earth checks out this situation with the rocket ship, but the rocket ship's moving, so they have a strange situation, and their time goes slower. There's a phrase you'll see quite a bit. I think it shows up in some of my notes, just briefly in my PowerPoint. It's a nice way to remember how this works. Moving clocks move slower. Okay. That implies that on Earth, we know the real time, and there's something weird going on in the rocket ship. Reality is, the rocket ship thinks time is normal and looks at Earth and says, wow, there's something weird going on there, and they're both right. It isn't just that moving clocks advance slower, and the clock is just an analogy, right? It's just a symbol of the fact that time is moving slower on the rocket ship. It's not just that, but time is moving slower in both reference frames. So from the rocket ship perspective, looking at the Earth, time is moving slower there, and they're both correct. So basically, we lose the ability to communicate. We have different realities if we're in different frames of motion or different frames of continuous motion. And we want to be careful to edit out of our language. I'm hoping I do pretty well with this. Any vocabulary that implies one situation is more valid than the other. One situation is real, the other one is just some weird situation. All reference frames are completely valid. They both experience reality, they're both correct, and they're different. Okay, so we'll try and speak relativistically correctly, and then see how we do. Now, this is the important lesson here. Both perspectives are right. So do you remember our first day of school last August? I asked a series of questions, and one was I walked across the room, and I walked to the east, and I said, okay, who's moving faster, you guys or me? And people looked at each other like I was crazy. A couple of people raised their hands. Somebody yelled out, you're moving faster. I said, great. Now, how about when we take into account the motion of the Earth, right? If we do that, now the Earth is spinning from, I guess, to the east, right? And now I'm going really fast because I'm going with that motion. But if I turn around to the other end of the room and I walk backwards against the rotation of the Earth, sitting still, you guys are moving faster than I am. I'm moving the rotation of the Earth. At the equator, it's 1,000 miles an hour. Here at the 42nd latitude and lander, it's probably very close to, I calculated it, 700 miles an hour. And then when I'm walking toward the west, I'm moving at roughly 700 miles an hour minus the speed of my walking, and sitting still, you guys would be going faster. Who's right? Well, it just is relative. It depends on motion with respect to what? Motion with respect to the floor and the walls and the chairs? Well, then I'm going faster in both situations. Motion with respect to the Earth's exterior rotating around its axis, well, then it depends on which direction I'm moving. Maybe sitting still, you guys are moving faster, right? And if that analogy is helpful, I have a couple more silly analogies. So this goes back to classical Newtonian physics and Galileo and those folks. And they understood that when we talk about motion, it's really the case that you need to take into account two velocities. If there's a collision between a car and a tree, or car and a car, you need to know how fast is the car going. And first car, and how fast is the second car going. If there's a collision between a baseball catcher's mitt and the baseball, right, you need to know how fast the mitt was going too. right? So the difference in speed has to do with the two different motions. And then the perspective from the hand inside the mitt is like, ow, man, that ball was going really fast. Similarly, the ball flying in is going to get stopped abruptly and say, wow, that mitt was moving really fast. And both perspectives are correct. Imagine this. You got a dog in a car. Dog loves going in the car. Dog gets in the car. Parents, the owners never let the dog jump out the window, so the windows are always up. Dog gets in the car. Doesn't matter if it's raining or if it's really sunshiny. Dog gets in. All of a sudden, there's a loud noise. There's rumbling and vibration, and there's kind of centripetal forces and stuff, and the world starts whizzing past the windows. And then, noise stops. They open up the door, and there's a different location around. The humans are so smart. They created this machine. You get in. It's a little bit noisy and stuff, but it makes the world move to you. And we want to go visit the dog park. Cool. That trip usually takes about 5 minutes. We get in the car. We get out. There's a different location outside. It made the world move and brought to us the dog park. Right? From the dog's perspective, that's maybe what a car feels like, or traveling in a car. Here we got another dog. Here we have a guide dog on an escalator. God, these humans are so smart. They got this little machine. I want to go downstairs at the elevator, right? And have you seen it at airports? They have these horizontal human transport sidewalks where you stand. You got to go a quarter mile to your terminal, like in Denver at DIA. And so you just get on this little escalator and you go horizontally and don't have to work. You put down your luggage and it just does the work for you. So we have an escalator. We got this dog thinking, people are so smart. I get on this machine, it vibrates, it makes a little bit of noise, and it just brings the basement floor up to me, or my terminal. Just like, I'd like to go to my terminal, please. You hit this button, and whoop, it brings the terminal to me. Be a reasonable perspective. Similarly, in an airplane, looking out the window, you get in this machine, you sit down for a while, somebody comes by and offers your owner peanuts and a drink, and you just have to sit there. There are all these people and weird smells and sounds, but you can look out the window and you see the whole world fly by, and then you get off and you're in another country or something, right? Airplanes and people, so smart. Okay, so the concept is, in the theory of relativity, there are two perspectives, and they're both valid. So if we have motion, it's relative. I see a rocket ship flying by. It looks to me like it's in motion. Rocket ship looks out the window and says, well, there goes Earth. And it looks to the people in the rocket ship. They're walking around. They're listening to their podcast on their phones. They are, drinking coffee, reading a little bit, occasionally checking with this automatic steering system, and they're looking out the window, seeing the universe fly by. As far as they got to get up and they walk to the bathroom, as far as they're concerned, everything in their world is normal. They're just kind of trapped inside this machine for a while, and the locations outside are being changed, and the Earth is flying past. Okay, so motion is relative, and in all parts of the universe, everyone has the same right to claim that they are stationary, and that the rest of the universe is moving. So just the concept of motion is tricky. You could make the argument that if two things pass each other, that one is still and the other is moving, and you could switch the roles and say, no, actually the other one feels like it's still. And that's a really important consideration here. So here we have two clocks. I have here two timers. I don't know how helpful this is or not, but I've got these things. They look like clocks. And we're going to use a couple of analogies that refer to clocks in different locations or different reference frames and in different states of motion. So here's the situation. These two clocks are in different states of motion, and they pass each other. From A's perspective, hanging out in space, B goes whizzing past. I think looking at your screen looks like B goes to the left. A feels stationary and everything seems normal in its experience, and they see this other clock B whizzing past to the left, sorry. From the reference frame of A's perspective, I'm at rest. B is moving, therefore B's clock is running slower. Time in that reference frame is different, and it's slower than mine. So here's that phrase, moving clocks run slowly. It's not relativistically correct. It's just a nifty way to remember stuff. It implies that actually I'm stationary. My situation is the real time, which is, of course, immediately an indication that you don't really understand the theory of relativity if you use language like that, if you explain something in that way. And here's why. From B's perspective, B feels like, oh, I'm at rest. And oh, look, there goes A whizzing past to the right on my screen or outside the window of my rocket ship or whatever. Therefore, since A is in motion, it must be experiencing in its reference frame time at a different rate. It should be experiencing time slower than I am. Both are correct. They're just different. They're different perspectives. They're different realities. And there's no magic trick here. There's no cool math trick. We're going to do a little math later. It's not some weird peculiarity of a math problem. It isn't something about the mechanics of the clock. There's extra friction or gravity in one situation because of the acceleration. It isn't some weird force holding back the hands of the clock. What's happening is time itself is just different, and the clock symbolizes that. Time moves slower in the other situation because of its motion. And it is the case that both perspectives feel the other one has slower time. How is that possible? It is. It just is. That's part of how, not only is it weird that time is different, but both situations, both reference frames would look out at the other clock and say, oh, but their time happens to unfold at a slower rate. And they're both right. Now you understand the twin paradox. Beforehand, we talked about the twin paradox. All we really did was introduce the concept of time dilation, that they experience time differently. Now, to review, the twin paradox is we have a situation with two brothers. Let's say in this case, looks like the drawing is that they're male, two twins. So they're born about the same time. They're about the same age. One gets in this rocket ship, is an astronaut, takes off 10% the speed of light or something technology can pull off in this imaginary universe, turns around, flies home 10% the speed of light, gets out. Because of that motion, because that rocket ship and its occupants were in this other reference frame, traveling at a much greater velocity, 10% the speed of light, time moves slower for them. So the astronaut twin had fewer birthdays and didn't age as much. Returns home years later, hops out to give his brother a hug, and the observer on Earth, the twin who stayed behind, is older because time continued at the same rate as it had been on Earth, and that brother had more birthdays. The paradox is that wouldn't it also be reasonable to say that the rocket ship was some weird transportation machine, and you get in, it makes this loud noise and rumbles, and whew, the universe starts moving past. You can see it outside the windows, and it brings your destination to you. And the outside universe is in motion, whereas you're stationary inside your rocket ship, and everything's normal, and you drink your coffee. And therefore, the Earth's time frame was in motion, and time unfolded at a slower rate there. So when the astronaut got out of the rocket ship to give his brother a hug, the Earth twin should have been younger. Time would have moved slower on Earth, and fewer years, fewer birthdays would have transpired, and the astronaut would be older in that situation. Shouldn't both be true? But they can't both be true. Here's the paradox. It seems like a contradiction. You can't have it both ways. And in fact, you can't. When they meet, one is going to be older, right? Okay, here's the situation. We believe time dilation happens just as we described. The math is First half of the math is very simple. We'll do some examples of that. The second half is more complex, and we won't. And I'll just tell you the answer and explain how that works. But a classic time dilation situation isn't as complicated as this rocket ship one. I'll just jump to the summary here. The reason this is different, this paradox seems like it says, wait a minute, no longer does this relativity stuff hold up. Actually, it does, but it's more complex because the person on Earth experienced one reference frame, one type of continuous motion, therefore one type of time. The astronaut experienced three. First, on Earth, sharing the same reference frame as his twin. Then, accelerating up to 10% of the speed of light and moving away. Then, turning around, changing reference frame into a third reference frame, and then accelerating up to the speed of light, now in a negative direction, returning back to Earth. Three reference frames. This person has changed into three frames. They call that frame jumping. And it's because of that things are no longer symmetrical. And one brother has, in fact, experienced time slower and aged less. And one brother has remained on Earth, experienced only one time frame, only one situation of continuous motion, and therefore only one continuous experience with the rate of time, and aged quicker. Okay, so when we are specific and trying to be as accurate as possible in discussing the theory of relativity, or specific examples therein, we want to be careful about our language and avoid ever implying that one environment or situation has more validity or really understands, what time is. That there is no one reality that's correct. In fact, there are going to be different situations creating different realities, but all realities are valid and true. We also want to be specific about location. When we're talking about these things, when we're doing math problems, we want to talk about, okay, so this is what I would measure from this particular perspective in this time frame, right? And then switching to this reference frame now, I'd measure a different number. So we always want to be talking about, when we're discussing examples of relativistic difference, which observer, which reference frame are we discussing at that moment? Okay, so we'll do our best with that. Here's an example. Imagine we have 3 clocks. I'll say here's 1 clock, and then I have my other 2 clocks. We're going to synchronize them so they all read the same time. This is no easy thing. I'm not going to waste a lot of your time, but imagine I have these 2 clocks. I'm just going to simplify it. Why can't I have them together, get them to read the same time, set the back here, adjust this one. Okay, now they're identical, and then separate them into different parts of space. Why can't I have them synchronized when they're together and then move them? Well, by moving them, we mess up their reference frames, and no longer they're experiencing time the same, so they're no longer synchronized. It's complicated. There are ways to handle that. I guess they're not simple, but I'll just throw out a couple. We could have these 2 clocks separated in space. Let's say that they are let's say 10 light years apart, and somewhere in the middle, exactly equidistant, we send out a light burst. It travels the speed of light. It goes in both directions to both clocks, and we just program them so that when the clocks see the light burst, they start their timers at 12 o'clock noon. Right now, they're in different places, and they've been set to the same time. There are some things we can do that are kind of clever and make that work. So let's say we have them synchronized. And we have them synchronized with a 3rd clock. The deal is that from, in this example now, I'm not going to do this with math. You're going to be scratching your head at the end a little bit. And I'm just going to ask you to trust me that the situations I'm describing and numbers I'm I guess, alluding to are 100% backed up by many calculations by many different people and many scientists. And so this is a teaching example you can find on the internet, I bet. And we're not going to do the math ourselves, but we'll do some math here in a little bit. Okay, so from A's perspective, A's hanging out in space, and these two clocks pass. First goes B prime, B1, and then B2. They're on the same trajectory, moving the same velocity. They're separated by space a little bit. So first B1 passes, and then B2 follows. Okay. All three clocks have been synchronized. The situation from B's perspective, they're in separate locations, and they see A whiz past. So A passes B1, and then at some later time, A passes B2. Now, in this situation, from B's reference frame, both B1 and B2 feel like they're at rest, they're stationary. They've been separated from each other, but they are at rest, and A is moving past. Clear? Easy enough. The concept here is that events that are simultaneous in one frame of reference are not in another. In fact, when we're talking about motion perpendicular to those events, parallel to the direction of motion of those events, they cannot be simultaneous in other frames of reference. If the motion is perpendicular, it can be. So, from B's frame of reference, B1 and B2 are perfectly in sync. They see A moving and say, oh, time moves slower in that reference frame. And they can see, first of all, as A passes B1 and A passes B2, they can look at their own clocks and see how much time passed. But because A itself is a clock, right, they can actually read A and say, wow, isn't that weird? That same time interval, in A, we got a smaller number. Makes sense. A is in motion, and time is unfolding at a slower rate, so A would clock a smaller amount of time between those two events, when A passed B1 and then when A passed B2. So far, so good. Here's where it's weird. From A's frame of reference, A looks at the clocks. They pass, first B1 passes, then B2 passes, and A records the time difference. And first event, second event, okay. I know what that time interval was. A now looks at the B clocks and reads them and says, wow, that's weird. We got different numbers. That also makes sense. Everyone would agree on that. But from A's perspective, time moves slower at the B clocks too. Here's what A would see. A would see that B1 and B2 are not synchronized, that somehow the synchronization didn't work at all. What everyone else thought was simultaneous was not simultaneous. And B2 is set ahead a little bit. It's sort of farther in the future. So now we see them passing, and we record a different time there. And what we see is the time gap is bigger. And the reason is B2 is not set to the same time as B1. They're not synchronous. Basically, those events weren't simultaneous. So that's why it's possible. And there's all sorts of math which will show that. Let me just go back here and say, one of the things that people can do mathematically is say, we're going to have a signal through this trip. Imagine this is the same thing now as our rocket trip, right? We can actually have a light pulse be sent from one observer to the other observer in the other reference frame every minute, every year, something like that. And then count them up, what the other observer receives. And what we find is, again, these different situations. With the rocket ship, we see, oh yeah, the rocket ship that took off, turned around, and then flew back to Earth had receive fewer light pulses. Everywhere we calculate the math, we see there were fewer years there, and there were more years on Earth. Here what we see is, in both cases, each observer feels time is this much, and in the other situation must be less, and they're both correct. So mathematically, this holds out. Because of the weird situation about the simultaneous events of synchronizing the clocks not being simultaneous in the reference frame of clock A, there isn't a contradiction. It could work out. Here's another example. I'm hoping you can read this yourself. The picture here is from Salvador Dali. Some of you love art. Some of you know his art. He was born something like 5 years before Einstein. I think he was born in 1904, maybe, and he was 1 year old when Einstein published his paper on the theory of special relativity. Regardless, the guy was an artist. He was brilliant. Even though he was an artist, he loved physics. Einstein was one of his heroes. This was one of the ground-shaking fascinations that rocked his world and influenced his art more than any other. And so this explains this theory of relativity, and time dilation specifically was so fascinating to him. He painted it into a lot of his work, and it's one of the reasons he has all these strange things happening with clocks in so many dozens of paintings of his. So some of your art lovers might enjoy that. We have, science imitates pop culture, and pop culture imitates science. We have that happening a lot in life. Here we go. This is now the Lorentz factor, which is the way in which we can actually do a little bit of this math ourselves. Now, this is a simplified version of the formula. Lorentz actually, some Dutch scientist mathematician, preceded Einstein by 50 years or so, and discovered some formulas that he didn't fully understand that Einstein was able to explain with the theory of relativity. We can use the Lorentz factor in this simple version of his formulas to figure out, well, so how much does time slow down in that other reference frame? Basically, the Lorentz factor is a translation. You know, when you're having a conflict with a friend, it's hard to put yourself in someone else's shoes. In the theory of relativity, it's crucial, and it's so much harder. This is the translation that lets us, from one reference frame, calculate what would be going on in the other reference frame. Okay, so here on your screen, we have t prime, that's with the little apostrophe, I guess, equals t times the square root of 1 minus velocity squared. T prime equals t times the square root of 1 minus velocity squared. Okay, so t prime is how much time's gone on in that other reference frame. Okay, well that equals, to calculate, to find out how much time has transpired on that moving rocket ship, I take my own time. That's the regular t times the square root of, and I just need to know how fast is the rocket ship going. Rocket ship's going at 90% the speed of light, 0.9 c. Okay, I take 0.9 c and I square it. I take 1 minus whatever that is. I take that difference and I get the square root of it. And I multiply that times my own time. Now I've got this conversion factor, and I can take my time and figure out how much less time has transpired on that moving rocket ship in its frame of reference. Okay? So we're going to do some problems like that. We have a rocket ship. From Earth's reference frame, the rocket travels at 80% the speed of light. And the trip takes 12.5 years. Let's say this goes out to an exoplanet, some newly discovered planet that's orbiting around some other star, so a different solar system. 6.25 light years away, turns around, comes back to Earth. Total trip time took 12.5 years. Okay. So V equals 0.8 c. I don't know why there's a comma there. And the decimal point there is overlapping a faraway galaxy on this picture. Hopefully you can see that as not 8, but it is just under the number 1, 0.8, the speed of light. T equals, that's the time I experience on Earth as an observer watching this rocket ship leave before it returns. 12.5 years. Okay, and I got little pictures there in the bottom. Now this is from Earth's reference frame. You'll notice the picture of the Earth is a little bigger here. There's my, okay. We're going to do some math now. V equals 0.8 c. Velocity equals 80% the speed of light. T, or the time I experienced observing this from Earth, 12.5 years. Now to get distance, we're going to have a formula, use a formula which is old Galileo, Newton kind of stuff. And we used it when we talked about our sledding a little bit. Distance equals velocity times time. For people's brains work like mine, even something simple like distance, velocity, just hearing those things said quickly, they just blur in my mind. I'm not tracking it. Sounds reasonable. I say, and then later I can't, what did you say? Distance equals velocity times prime? I don't know. So distance equals velocity times time. If I want to know how far something is, I just need to know the speed and how long it was traveling. If I'm going 60 miles an hour in my car, here's an analogy which maybe will help you track. Oh yeah, distance equals velocity times time. 60 miles an hour in my car for half an hour, I only went 30 miles. If I go for a full hour at 60 miles per hour, then I go 60 miles. If I drive for 2 hours at 60 miles per hour, I'm going 120 miles. So my distance is my velocity, 60 miles per hour, times however long I did that. Right? Okay, distance equals velocity times time. We know the velocity is 0.8 c. We know the time. The trip required 12.5 years. If you take 80% of 12.5 years, or you multiply 12.5 times 0.8, you get 10. Okay, that is the distance. This exoplanet must have been 10 light years away. 5 light years away. It went 5 light years, turn around 5 light years back, total distance traveled of 10 light years. And if it had been going the speed of light, it would have taken 10 years. But it was going a little bit slower, only 80% the speed of light, 0.8 c. So it took a little bit longer, 12 light years, 12.5 years instead of 10 years. Okay, so there we go. We have velocity, we have time, and we have distance. Now you see in green I have rocket trip. We're going to do that again. And now you see the exoplanet image is bigger. We're going to do this from the reference frame of the exoplanet, or from the rocket. So here we have the rocket's frame of reference. It's still traveling at 80% the speed of light. Now, how long does a trip take? How much time is required from the rocket's perspective? So we're going to use our same formula, the Lorentz factor, and we're going to take our new numbers. The velocity hasn't changed. Remember, velocity can't change. We're talking the speed of light is always the speed of light. So 0.8 c is always 0.8 c. The rocket traveled at 0.8 c. Now, for the formula, we need to know the velocity squared. To use the Lorentz factor, I'm going to go back here. We need to know our time and the velocity squared. And then we can take this 1 minus the velocity squared and the square root and multiply times our time. We can find out how much time transpired in that other reference frame. So v squared equals 0.64. And the time we experienced from our reference frame was 12.5 years. So let's do the math now with the Lorentz factor and see how long that takes from the rocket's point of view. As we said, v equals 0.8 c. So velocity squared equals 0.64. The time from our reference frame was 12.5 years. And there's our formula. T prime is going to equal the Lorentz factor times our time there. So T prime is how much time was required for the rocket ship, how much time was experienced by the passengers on board the rocket ship, what was happening there for their reference frame. So we want to figure out how much time transpired for them. We're going to multiply by our time, 12.5 years, and then take that times the square root of 1 minus v squared. So we get 12.5 times the square root of 0.36. You can try this at home on your calculator. I recommend you do. You're going to have to do a math problem later, so this could be practice for you. You can check and see if I got the numbers right, and by having to go through each step, maybe it'll be a little easier when you do it on your own. Square root of 0.36 equals 0.6, so 12.5 years times 0.6 equals 7.5 years. So on the rocket, those 12.5 years were much shorter. They only experienced 7.5 years of time. So now we've used Lorentz factor and we've calculated how much time was experienced in another reference frame, the one of the rocket ship. We can use the same Lorentz factor. By the way, in formulas, you'll see the Lorentz factor shortened to just represent, it'll look like a Y. It's a Greek letter gamma. Gamma. People will, maybe if you see some videos on YouTube, people will refer to gamma. It's the Lorentz factor. And so we've got that figured out here. And we used it to multiply it by our time and find out that less time occurred, and it was exactly 7.5 years. Well, if it went for a shorter distance, if it went for a shorter amount of time and it was still traveling the speed of light, it couldn't have traveled that same distance of 10 light years. So we can use the Lorentz factor also to see how much space was contracted, how much space was shortened. It had to go a smaller distance too. That's also a result of our understanding now that since the reality is different reference frames experience different motion, while the laws of physics are absolute, time isn't the same everywhere and space isn't the same everywhere. Let's talk about space now. So what distance did the rocket travel? Now first we got to get a distance that we thought it went, right? Well, we did that already. 10 light years was the distance. Distance equals velocity times time. We talked about that. 60 miles an hour times 30 minutes or half an hour equals 30 miles. So we went 0.8 light years in a year per year. That was our velocity. And we did it in 7.5 years. That's what the rocket ship did. We now are using their time. So from their perspective, going 0.8 the speed of light for only 7.5 years, they could only travel 6 light years. Different time. Here's this comparison. So you can see on your screen on the left over the symbol for the Earth, we have the velocity of the rocket ship. We all agree was 0.8 c, 80% the speed of light. The time we thought it was gone was 12.5 years, and the distance we calculated to the exoplanet and back was 10 light years. From the exoplanet's point of view, same speed, but the time they experienced was less, 7.5 years, and the distance they traveled was less. From their perspective, it was 6 light years. Very cool. All right, not difficult math, just some algebra. Let's just take a look at this. Here's a graph of Lorentz factor. You can see on the y-axis there, on the left of your screen, it's written horizontally, but that's a y. It's the Greek letter gamma. That's the Lorentz factor. It increases as it goes up. On the x-axis, on the bottom there, going across to the left, is the speed, the velocity, the percentage of the speed of light. And it never gets up to 1. It never gets up to the full speed of light, but it gets really close. That graph curves up and gets really, really close, but it shoots to infinity just as it approaches the speed of light. And if we look at 80%, if you look at the screen with your finger and touch where it says 0.8 and go up, you'll see that the Lorentz factor would be just a little bit less than a factor of 2. In fact, we found that the time experienced from the reference frame of the rocket ship was a little more than half what we thought happened. And the distance it traveled from the perspective of the rocket ship was a little bit more than half than what we thought happened. And you can see why we're dividing by something that's just a little less than 2. So it looks like our numbers are good. Lorentz factor affects both time and space. When we see time is altered because of a different reference frame's motion, we call that time dilation. When space is altered in a different reference frame because of a different motion, we call that length contraction. And they go hand in hand. Whenever you have one, you have the other. Okay, so here's another example. Famous example, it's both an experiment to see if the theory of relativity works. It's also a demonstration to say, check it out, the theory of relativity works. And it deals with both time dilation and length contraction. Basically, in the upper atmosphere, cosmogenic rays, meaning high energy whizzing through space, like gamma rays, interact with air molecules in the upper atmosphere and they explode them. The shrapnel of elementary particles, like electrons, protons, get scattered like shrapnel. So that these collisions, gamma rays hit air molecules. And one of the elementary particles is something called a muon. It's in the same category as electrons, has the same mass as an electron and energy. It's called a muon. And this muon is a lot heavier than an electron. We can use it in a lot of experiments. We can use it to bombard other particles and give them energy or scatter them or blow them up, or whatever. Interesting. They aren't very common in space, but they get created in our upper atmosphere as energy from space hits us, and then they rain down, they shower down on the Earth. And these are radioactive. They don't last very long. They don't hurt you too much. Every second we have about 10,000 muons going through us. And they can cause some genetic damage and cancer, like any of the sun's rays can, like ultraviolet ray can. And the incidence of cancer from them or genetic mutations is very small. I think that sunscreen helps, just like it does with ultraviolet light. But it's happening all the time. They actually are really abundant in upper space. So planes and astronauts, I don't know, satellites get this kind of energy a whole lot, but not many of them make it down to Earth. In fact, none should. We can know experimentally how long these things last, how long it takes for the radioactive decay. It's just milliseconds. I mean, just microseconds, nanoseconds. They don't last very long. And going those incredible speeds that they go, really close to the speed of light, even at those speeds, they shouldn't make it to the Earth. Here's the experiment. This guy, Frisch and Smith, two men, did this in the 70s. It's been repeated. Mount Washington is a huge mountain in New Hampshire, I believe. It goes right up from, not far from the Atlantic Ocean, up to 6,000 feet, over a mile high. It's really rugged for mountaineering, technically difficult. There are a lot of accidents and fatalities that happen there. It has vicious weather, horrible snowstorms and blizzards, and some of the highest velocity wind ever measured on Earth. So they go to the top of Mount, I think there's a road to the top of it too. Go to the top of Mount Washington, 6,000 feet. They get a little detector. They measure the amount of muons they get. Muons, they get about 600 a hour, I think. None should make it to the bottom if they go down to sea level and get the same detector out. They shouldn't get any, really. They should have all decayed. They live so long, so short, so briefly that by the time they whiz down that low in the atmosphere, they should have all ceased to exist, and the detector shouldn't pick up any. At the bottom, they measure 400 an hour. The muons are traveling at, and there's a star or galaxy right behind that decimal point. That's 0.99 the speed of light. 99% the speed of light, 0.99 c. But because they're going so fast, they've got time dilation and length contraction happening at that speed. To the bottom, that 6,000-foot mountain only seems like 700 feet or so. I don't have the exact numbers here, but we're going to do some math with this. Since the mountain seems so short in their reference frame, they haven't had time, they haven't had the distance needed for them to all experience radioactive decay, and there's still about 400 of them left when they interact with or collide with our detector that collects them and counts them. And so if you take relativity into account, the weird result we get experimentally, the data we collect, makes perfect sense. It's exactly what we would expect. If you don't understand relativity and the fact that these things are going almost the speed of light, well, then you wouldn't be able to explain this. Okay. Let's practice our math real quick. We're going to use Lorentz factor. First, we're going to get a distance from their perspective. Now, we know that in our reference frame, the distance is 6,000 feet. That's the same as 1,828.8 meters. I just used the internet to convert that. We know that the speed is, I have a discrepancy here. The velocity is 0.999 the speed of light. So we're going to use that one for our math. Now, I rounded off the speed of light because I said when we do math, we're just going to say it's 300 million meters a second. It's just a big, round, easy number. So it's not exact. But I rounded that up. And when I get that number times 0.999, I get this smaller number, slightly smaller number, 299,700,000 meters per second. So now that's the velocity we're going to use for our math problem. The muons are traveling as they drop in the atmosphere. Now, time is that same formula. I know the distance already. I told you the mountain was 6,000 feet. And I know the velocity. I told you the thing was going, the muons are traveling at 0.999% the speed of light. So what I don't know is time. And in order to use the Lorentz factor to convert and figure out what's happening with time and distance in the reference frame of the muons, I need to know how long it took for the trip in our perspective, in our reference frame. So I'm just going to reorganize this equation and solve for time. So time equals the distance divided by the speed or the velocity. And I get this. The muons traveled as they descended through the atmosphere from the top of Mount Washington to the bottom. That 6,000 feet in our reference frame took them 0.00006 seconds. It's 5 zeros and a 6. Okay, pretty fast. And we would expect that. They're going almost the speed of light. Now, we're going to calculate the Lorentz factor. How long did it take for them in their reference frame, in the reference frame of the muons traveling at 0.999 the speed of light, t prime, their time, we would take the time it took in our reference frame, regular t, times the square root of 1 minus 999 squared. Well, I've got that number then a little different again. 0.99c squared is 0.01. The square root of 0.01 is 0.1, or about a tenth. So we multiply that times the time it took in our reference frame. And 1/10 of that turns out to be 0.0000006 seconds. 6 zeros and a 6. Okay? So it took about a tenth of the time. It was shorter. The trip was way shorter. For them, they experienced time moving more slowly. Now let's talk about the distance they traveled. We know what the distance was because it's the length of that mountain. 6,000 feet is the altitude of Mount Washington. It was something like 1,828.8 meters. So now we're going to find out what was the distance, d prime. So the distance in the reference frame of the muons. We have the velocity, which is the same still, 0.999 c, times the time they experienced in their reference frame. That's 6 zeros and a 6 seconds there. And what we get is 179.82 meters. Okay, less because they're going the speed of light, because they've experienced length contraction, they've traveled a smaller distance. From their reference frame's perspective, the mountain was shorter. That makes sense to us. That's consistent with what we've talked about. Now, if I convert that, I just went online and configured, well, what is 179.82 meters into feet? It's 590 feet. And by the way, if you want to see this same exact example, this classic experiment, in a really short, I think it's 4-minute YouTube video with these cool drawings, it's one of those where you just hear the narration of some young guy and you just see a hand doing art. And you might find that helpful to understand what I just said. Let's just check our work here. I didn't finish my point. There's the YouTube link if you want to watch that. You can pause, write that down, check it out if you're interested. Okay, so let's check our work. We have the Lorentz factor. Remember, that was the square root of 1 minus velocity squared, which turned out to be about 1/10. Well, we knew that in feet, when I gave you the altitude of Mount Washington at first, it was about 6,000 feet, and 1/10 of that is about 600 feet, and that's about what we calculated. We just did some math and came up with 590 feet. So you can also just calculate the Lorentz factor, gamma, and multiply it by the distance you experienced in your time frame or in one time frame, and then multiply it by the velocity, the time experienced in the other frame of reference, and get what the distance would be in that other reference frame. So how do we do that? Well, first, we found the time in our reference frame. Second, we found the time in their reference frame. And third, we found the distance in their reference frame. You can rewind and you can review this, pause, and look at the math examples. You can take out your calculator and test both examples I gave you. Here is a math question for you. There are only 2 questions for today's video. Here's the first one. It's a math problem. You have only one math problem, and then you'll have a little summary I want you to write. You've heard of CERN, maybe, this particle accelerator underneath Switzerland, in which we collide electrons going almost the speed of light. And do all sorts of neat things, including hopefully maybe someday make a tiny little black hole which will evaporate in milliseconds, but we'll be able to observe. This is one of the ways in which we, by the way, synthesize elements in a lab. Most of the elements at the bottom of the periodic table only exist for a few milliseconds, and they've been created in this manner. So we take 2 particles and smash them together, 2 protons, or a few protons, smash them together and make some new thing. Okay, so we have one like that in the United States. Stanford has it in California. It's underground. And the track is 2 miles long. That's 3,218.69 meters. And we take electrons and things, smash them together at high speeds. So this track goes around and around and around and around. I want you to do the same math problem, assuming that the electrons traveling in the Stanford Linear Accelerator are traveling at 0.999995 C. 5 nines and a 5. So 99.9995% the speed of light. Okay, so I want you to find out, first you have to use the Lorentz factor and find out how long does that take them. Actually, first you have to use distance, figure out how long we would think the trip is. Then find out how long it takes from the perspective of the electrons, and then find out what is the distance. That's the ultimate question here. What is the distance from the reference frame of the electrons traveling through the linear accelerator? How far do they think that track is? All right, I'll put that problem here. You have to answer it first before you can move on with the rest of the video. And what I have now is a much easier to understand example of length contraction, which is mind-blowing, I think, and involves zero math. Okay, so now we're finally going to really, I think, help you understand that events that are simultaneous in one reference frame are not simultaneous in another reference frame. I like this. Okay, first we have to define the term event. So in terms of relativity, an event is anything that occurs in a specific time and a place. Not too complicated. Makes good common sense. If you're going to meet somebody for lunch, you say, oh, yeah, let's meet at McDonald's. You need to tell them what day and what time. They know where McDonald's is. They know the place. They also need the time. You need both of those bits of information to define an event. Okay, here's our situation. I love this. This is my second favorite thing in relativity. So we have two space shuttles pass each other. They're traveling at 10% the speed of light or something. Doesn't matter. We're not going to do math right now. And so in this case, I'm observing this. This is from the reference frame of an observer on Earth looking up and seeing these two pass each other in the air. And they're going the same speed. They're going in opposite directions. So one's going, 0.1 c, and one's going negative 0.1 c because it's the opposite direction. And they're experiencing length contraction, and we don't care. These are the same space shuttles, same design, same manufacturer. They came off the line the same year. Everything down to the manufacturer who made the bolts for the steering system. Everything is the same, and they are the same length. And now their length contracted a little bit, and they're both length contracted the same amount. So they're the same length still, and they pass each other. And I look when I see them pass each other, and it would look a little bit like this. And you can see the upper shuttle has a nose on the left side of your screen, and at this moment, it's passing by the tail of the lower shuttle. That's for the first event. The second event is the fact that the other ends of the shuttles are passing at the same moment. Simultaneously, the tail of the upper shuttle is lined up with the nose of the bottom shuttle. Okay, so those are our two events. And anybody observing this would agree, oh, they're the same length, both the left ends and the right ends lined up at the same time. They were simultaneous. Agreed? Okay. Now, here's a second reference frame. This is now from the perspective of the upper shuttle. The upper shuttle is looking out the window and says, oh, look down there. There's this other shuttle. There's a second shuttle passing us. From the perspective of the crew on the upper shuttle, they're drinking their coffee. They're on their cell phone listening to their podcast. They're checking the autopilot navigation system. They're walking to the bathroom. They experience some noise and vibration, but the length of their cabin, the length of their bodies, the time it takes to talk, to breathe, for their cells to age, everything is normal for them, right? As far as they're concerned, their reality is the only reality, and everything's correct. It almost feels like they're stationary. And they look out, they see this other shuttle pass below them, okay? Now, they look and see the other shuttle is moving, and therefore its length contracted. It looks shorter than them. In this situation, from the second reference frame, the perspective of the upper shuttle, they look down and they say, oh, look, this little stubby shuttle is passing us. And as it does so, right, they first start passing each other, and then the other one's much smaller, right? It's the one at the bottom is much smaller. I should do it this way. It looks like the upper shuttle's nose passes the tail of the lower shuttle. Only later will the lower shuttle's nose, there we go, pass the tail of the upper shuttle. So now we have two different events, and they're separated in time. They didn't happen simultaneously. I hope that is something you can accept. You have to accept these assumptions that this discussion about length contraction is real. But I can assure you that scientists, physicists all over the world believe that this is how it works. So now we have a situation where the observer on Earth in that reference frame was convinced both the left and right ends passed each other at the same moment. Those two events were simultaneous. Now we have, and that's reasonable, totally valid. Also, is this different reality on the upper space shuttle? We see those events were not simultaneous. That one happened first, and then the other one happened second. Okay, here's a third reference frame. From the perspective of the lower shuttle, oh, look, there's another shuttle passing us up above. It's moving really fast. I guess it goes this way, right? And it looks length contracted. Now it looks like the left ends pass first. The tail of the upper shuttle passes our nose first, and then the nose of that upper shuttle passes our tail second. Here's what's crazy to me. We have a third perspective. It's also valid. It's 100% real. It's different. And in this situation, not only are those events not simultaneously, but we would argue about which one happened first. We'd say, no, 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 you got the order all wrong. The left ends lined up first, and then the right ends lined up. So we would argue and disagree about the sequence, and all three perspectives are right. I love that. If you want to watch a little animation on this, Nova's got a good one. I've got a link for you there. There's tons of stuff on the internet if you want to look up time dilation or length contraction. You just go to YouTube. You'll find, choose among many, and there are some that have math. Most have no math at all. Fun, huh? So this is relativistic simultaneity. You will impress people everywhere you go when you talk about this. If they don't start hitting you, they will be impressed. Ready for this? So can my birth and death be debated? Could someone else in a different reference frame argue about which one happened first? Does this change our understanding of causality, that A led to B? That's a pretty big part of our reality. No. So this whole thing about, we're going to argue not only about simultaneity, but the sequence of which event happened first, which one happened second. They only happen for a specific class of events, right, that are simultaneous in some reference frames. There is nobody in the universe who would say that I was born after I died. The situation is, we can argue about the sequence of events if they happened in places that were really far apart in a relatively short amount of time. If things happened the reverse, my life, I've traveled around, basically I've been stuck on this planet, so none of the distances, doesn't matter how many countries I've been to, I never got to go too far from the place where I was born. So I was born, and at some point I'm going to die, and they'll all be in relatively close proximity to each other, separated by a good amount of time. Nobody's going to argue about that. Our next topic, which is my favorite thing, is about past, present, and what Einstein calls the elsewhere. And there's no math involved at all. I think you're going to love it. Thanks for tuning in.